All right, I think it's time to get started, right? Welcome, everyone. Welcome to the second session of Emsoft, which is on mobile and resource constraints systems. My name is Kasım Sinan Yıldırım. I am with Trento, Italy, and it's my pleasure to get this session. Let's welcome our first speaker in this session, Osama Khan. I would like to give a brief introduction about Osama. Osama earned his bachelor's degree in computer science from Busan National University, South Korea in 2021. He is now pursuing the PhD degree at Sungkyunkwan University in South Korea, and his research interest covers the system software for efficiently supporting AI services. And today he's going to present the paper titled DCAPO, an on-device learning scheme for memory-constrained embedded systems. The floor is yours.
All right. Hello. Okay. Hello, I'm Osama Khan, and today I'm pleased to present our work, DCAPO, an on-device learning scheme for memory-constrained embedded systems. So the use of deep learning models in microcontroller embedded system is rapidly increasing. And there have been several successful applications of using DNN models inside microcontrollers. For example, they're used in health monitoring systems to predict the disease onset. They're used in wildlife to analyze the animal behaviors, and they're also used in smoke forming to analyze the environment. Now, there are some of the examples of using DNN in microcontrollers. However, the data distribution that the model faces during the training differs from the data distribution that they face in actual real world. So this is the data distribution, and you can see here we have the training data has two different features, feature 1 and feature 2, and this is the boundary that the model learns. Now, when the model is deployed in real time in a real world environment, what happens is that there is some sort of distribution change in the incoming data, and this distribution change causes the model to incorrectly classify some of the examples. And because of this distribution change, there can be accuracy loss, and this accuracy loss is up to 30%. And in order to overcome this problem, we need to fine-tune the model with the actual input data. Furthermore, the microcontrollers that we are targeting, they have several operational challenges. First of them is erratic energy supply. So these microcontrollers are either powered by batteries or they're powered by energy harvesters. And in both the cases, the amount of available energy is quite limited. So the microcontrollers need to efficiently utilize the available energy. Second, most of these microcontrollers are deployed in real-time situations where the execution time is quite important. From the time the input data comes until the response is generated, it should be within some specific time frame, and therefore it puts another limitation or another constraint on the microcontrollers, which is that they should be timely and predictable. And finally, the microcontroller that we are targeting, they have quite small SRAM size. So you can see the SRAM size can range from 40 kilobytes up to 256 kilobytes, and that's it. So these microcontrollers, they need to efficiently utilize their memory when they're executing a program or an application. All right, so on-device learning is actually used to fine-tune the model to overcome the accuracy loss. And in order to do that, we just take the data and give it to the microcontroller, and the microcontroller learns this new distribution. And this will help us to overcome the accuracy loss. Now, on-device learning uses backpropagation for fine-tuning the model. And I'm going to give you a brief explanation of backpropagation. So in backpropagation, usually there is a forward pass and backward pass. And suppose we have DNN models with 6 different layers. What we do is we take the input, we give it to this DNN model, and then we compute the output of the first layer. We take this and give it to the second layer, compute the output of the second layer, and so on, until we have successfully computed the final output. Now, note here that we need to store the output of all these layers in the memory during the forward pass. Why do we need to do that? Well, we need to do that in order to perform the backward pass. When we want to perform the backward pass, we take the loss and we give it back to the model. But now in order to update this last layer, we need to have the output of this second to the last layer. So if we want to update the 6th layer, we need to have the output of the 5th layer. And this is the reason why we need to have the output of all these layers computed during the forward pass inside the memory. So you can see here, we're going to take this output and update our layer, and so on until we have successfully updated all the layers. Now this is quite problematic. Why? Because if we want to store the output of every single layer in the memory, we need to have quite a lot of space. And this is not possible in microcontrollers because they have very small amount of SRAM. So, excuse me. All right. So we cannot store output of all the layers in the memory. And furthermore, these are the 5 different applications that are commonly used in microcontrollers. Tiny VGG used for action recognition, depth estimation used for obstacle detection, DSCNN for speech command, FOMO for car detection, and MobileNet for visual wake word. Now, if you look at the amount of memory consumed during inference, the maximum is up to 80 kilobytes. But if you look at the amount of memory required for backpropagation, it's quite high. For MobileNet, we almost need 2 megabytes of memory. And this is not possible because microcontrollers are usually equipped with very small amount of SRAM. So you can see that the amount of memory required for backpropagation is 9 times more than inference and is not feasible in memory-constrained microcontrollers. So microcontrollers are also equipped with something called flash memories. And these are the secondary memory of microcontrollers, and they're ideal for read operation. They have more capacity than SRAM. And the problem with using flash memory is that if you want to write the data into flash memory, you need to perform an erase operation before that. And both this erase operation and write operation is quite time-consuming and energy-consuming operation. To understand this, we took a DNN model and implemented it using both SRAM and flash memory. And we found out that when we implemented it using flash memory, it consumed 4 times more energy than SRAM. And at the same time, it was 379% slower than SRAM. So it's not, we decided that using flash memory to just store the output of all the layers temporarily is not ideal for backpropagation. So far, we said that DNNs are used in microcontrollers, and then there's an accuracy loss because of change in data distribution. And to overcome this, we need to perform on-device learning. On-device learning uses backpropagation, but backpropagation requires a lot of memory, and at the same time, microcontrollers, they have quite small amount of memory. So the problem becomes, how can we execute backpropagation using small SRAM? All right, so we present Decapo, an on-device learning scheme for memory-constrained embedded systems. And our basic strategy is to recompute the output of a layer. To understand this, suppose again we have this backpropagation, and here again we are going to compute the output of all the layers, finally compute the output, use it to compute the loss, and then we are going to update the layers. Now here, note that, well, this is a simple example of neural network with linear structure. So in this case, if you want to update the last layer, we only need to have the output of the previous layer, all right? So in this case, since we have the output of the previous layer in the memory, what we're going to do is we're going to simply just carry on this and update all our layer. But note here, if we want to update only a single layer, we need to have the output of the previous layer only, not these outputs. So our basic idea is to just drop them and recompute them when they become necessary. So the new method would become something like this. We'll take the input, and this time when we pass it through the layer, instead of keeping it in the memory, we're just going to drop them one by one, and we will compute the output. From this, we will compute the loss, and now it's time to update the last layer. In order to update the last layer, this layer, we need to have the output of this layer, but the output of this layer was discarded or was removed from the memory. So what we can do is we can recompute from the beginning of the layer this way, and we will update the layer. Then again, we will compute and update. Again, we will compute and update. Again, until we have successfully updated our whole model. However, there is still limitation to this approach. So basically, we refer to this method as naive recomputation. And the problem with this naive recomputation is that it consumes a lot of energy and time. So to understand this, because flash was the slowest and it was the device that consumed a lot of energy, we started comparing our method to this flash. And what we did is we created 5 different models. The x-axis shows the configuration of these models. The 3C2F means that the model with 3 convolution layers and 2 fully connected layers. 5C means 5 convolution and 2 fully connected, and so on. R here means the recomputation, and F stands for using flash method. So you can see here, when the number of layers were quite small, maybe up to 5 and 7, recomputation was performing better than flash method. But as we increase the number of layers, let's say to 10 and 17 and 22, the recomputation started performing worse, both in terms of energy and in terms of time. And this is because of the quadratic overhead of recomputation. Specifically, every time you need to update a layer, you need to recompute it from the beginning of the network. And this is quite time and energy consuming. So what we did next is we said, all right, it's not like we don't have memory at all. Sometimes we have enough memory to store maybe 1 or 2 checkpoints. In that case, we say, why don't we just partition the model into multiple segments? So in this case, we are going to store the output of the 4th layer and the 8th layer. And we're going to call them the checkpoints. And next, every time we want to update a layer, we're just going to recompute from this checkpoint. So in this case, we are computing from this checkpoint. And in this case, we're going to compute from this checkpoint and until we have updated all our layers and so on. Note here that for the first segment, usually we need the input to update these layers. So this is called the segmented recomputation, which helped us reduce the amount of energy and time. However, this method is still performed worse than flash method. So to understand this, we again took the largest model from the previous experiment, and we divided it into 3 segments, 5 segments, and 7 segments. And as you can see here, both in terms of energy and in terms of time, the segmented approach did worse than flash method still. And this is because of the layers computational costs. Specifically, different layers have different computational costs. If you combine computationally heavy layers into a single segment and recompute them equally as the computationally light layers, you will end up having a huge energy and time consumption. So what we did next is we integrated this cost inside our final optimal segmentation method. And we also found out that if we have only a single segment, then what we can do is, and suppose that this layers or the candidate layer for the recomputation, what we can do is we can reuse this single checkpoint to store the output of multiple other checkpoints as well. This is because of the sequential nature of backpropagation. So during the first forward pass, we're just going to store the output of the last layer, the last checkpoint, and then we will perform backpropagation. Again, we will use the same memory to compute the output of the second checkpoint, perform backpropagation, first checkpoint, perform backpropagation, and backpropagation again, and so on. So using this method, we are able to actually use a single memory which was allocated for a single checkpoint multiple times. A note here that these are, if you are going to use a single checkpoint, then these forward passes are the extra computational overhead that we need to consider. So our final method is search all the possible segmentation. We just generate the list of all possible segmentation methods, and we will choose the one with minimum computational cost. And furthermore, since a neural network can be quite deep, and just searching and going through all the segmentation wave might take a lot of time. So what we did is we combined layers into a single layer, and this way it helped us to reduce the search time. And once the final method is found, we just kind of extract them back to its original position. This will reduce this can help to reduce the search time. So to evaluate our idea, we took the STM32F429Z1 board. It had Cortex M4 processor, 196 kilobyte of SRAM, and 2 megabytes of flash memory. We used 5 real-world models, and we explained the models before. And we did analysis with real-world DNN models. So we compared our method with a library called IFES, and this is an open source framework which is used to update the model inside small microcontrollers such as Arduino and those STM boards. And what it does is it just sequentially stores the output of all the layers in the SRAM if possible. So this is our final evaluation. As you can see here, D stands for decapo and A for IFES. And for all these 5 models, decapo performed better than IFES in terms of both time and energy. And furthermore, the difference is mainly because of the initial forward pass. When we use decapo does not need to store the output of all the layers in flash memory. So that's why it's consuming small time compared to IFES. And the same thing happened for all these 5 models. For MobileNet, we weren't able to actually execute it at all, even using flash methods. So we just implemented it using decapo, and it took around 80 seconds to actually complete one backward pass. And then this is the normalized energy, and you can see we found this. Excuse me, we found the same trend between decapo and IFES. And finally, we found out that for tiny VGG and DSCNN, the difference is not that much as compared to the other models. And this is because of their high computational cost per byte ratio. Basically, if a network has high computational cost, but it has small output size, then if we compare it with the flash memory, then it will have small advantage. So higher ratio means more computational compared to the write operations and less gain over flash memory. So to sum up, on-device learning is important for accuracy loss, but the problem is that it uses backpropagation and we have limited SRAM. And the question becomes, how can we implement backpropagation using SRAM? And our idea is to use recomputation through optimal segmentation. And we found that we have superior performance over the alternate options, such as using flash memory. And thank you.
Thank you very much for a very nice presentation, interesting topic, definitely. Do we have any questions? We have a lot of time for a couple of questions, I guess. Yes, please.
Thank you very much for the talk. It's about the last part when you merge some layers. I wanted to know what kind of merging you did.
So which, excuse me.
When you say you merge some layers to have just one layer?
So basically what we did is we found out that some of the layers is quite, they have, sometimes a neural network can be quite deep, okay? In that case, it reduces the...
So what kind of merge do you do? You merge 2 convolutions, 3 convolutions? Because since you do backpropagation, changing the type of layer can harden the optimization after to update.
Yes, exactly. Yeah.
So what kind of merging do you allow?
So we just took simply a single layer and merged it with this neighboring layer continuously. And then we found out that if the search time has reduced, we said, all right, we can just go with this method. And if the search time hasn't reduced, then we keep merging the 2 consecutive layers again and again. And we do this so if we are going to merge multiple layers, we imagine that, okay, the output of a single layer should, in the merge section, the output should be greater than all the other merged layers. Because this one would be then again would be a single segment. And we will store it in a layer, and then we will...
This I get mathematically. When you merge 2 convolutions, it can lead to a convolution. But if you merge a convolution and a ReLU and a max pool, what kind of layer does it get?
So in here, by matching, we are not matching activations with convolution layers. Our main focus was to match convolution with convolution and fully connected with fully connected layers.
That was my question.
Oh, I'm sorry.
Okay. So mathematically, you show some equivalence on the new type of layer you have now after merging.
Yes.
Okay, thanks.
Any other questions? Yes.
Yeah, hi, nice talk. So I was wondering, you only compared against, if your baseline is similar to yours.
Yes.
I was wondering whether you had looked at something like latent replay, which is used for continual learning, where you don't need to go through all the steps. So you have the first few layers, which are kind of, remains generic anyway. And then the last few layers are the one where the continual learning takes place. And so those are the latent replay is kind of the technique that you use typically for IoT devices. So I was wondering whether you have compared against, that kind of techniques.
So is latent replay similar to the transfer learning, where you just
something similar, yes. So you don't do for the whole thing. So you just do for the last few layers, right? And you don't store the images. You store something which is in a more compressed format. So you just store the features.
Yes, okay. Thank you for the question. So our focus was to completely, without any modification, execute backpropagation on DNS. Those methods, while they allow you to update a model, they always have some sort of accuracy loss. It's not like they are completely like the best option if you want to update it. So our main goal was, all right, take the best option, which is backpropagation, completely basic thing, and then try to implement this on using SRAM memory. Yes.
Any other questions? Maybe I can ask a very short question.
Yes.
Like regarding the practicality, I mean, at each iteration, you need to update the model, I guess, right? I mean, you perform backpropagation and do some updates. So in general, you need to interact with flash memory, right? Can it be considered as a kind of limitation for such kind of approaches, because each iteration leads to interfacing with FRAM, and you have a limited number of reads and writes in practice? Maybe you can use an external non-volatile memory to get rid of this situation, but I think it can be a problem in practice.
So we when we started this research, we assumed that, all right, flash memory, you can use them for updating the weights, even though they are not ideal, they have limited lifespan and all this stuff. But we continued from what previously research paper did, and we assumed that, all right, we can use flash memory to just update the layers. Basically, when you perform backpropagation, there are two types of gradient. One is for every specific to the layers, and one is specific to the weight. And you take the gradient with respect to the weight and update the every single layer. Now, these gradients and this weight parameter is kind of out of the scope of this research. What we mainly focus is on the layers output, which takes quite a large space. So our main goal was to actually minimize that and do not use, as you said, the flash memory and other memories because of their limited lifespan and other problems.
Do you have also a kind of pipeline, an automatized like software tool, something else like that, that I can give you a kind of, for example, neural
Yes, we are working on it, and soon we will release it on GitHub. So basically, we take the model from TensorFlow Keras. We we have a script that transfers it and finds the optimal segmentation plan and gives it to the Decapo framework, which will take them and execute them and perform the whole thing. Yeah, thank you.
If you don't have any other questions, we can thank our speaker and we can move on to next. So our next speaker is Wentong Li. Wentong received the bachelor's degree in computer science from Anhui University of Technology, China in 2020, and he is now a PhD student in computer science and technology from East China Normal University in Shanghai. His research interests include memory management, mobile computing, and computer architecture, and he is going to present the paper titled I-Aware, Interaction-Aware Task Scheduling for Reducing Resource Contention in Mobile Systems.
Okay, thank you, Ms. Yeah. Before my presentation, I want to claim that the original author of this paper can't be here because with the problem, I act as a substitute speaker, so I needed to receive my manuscript. So I hope it will be a problem for everyone. Okay. I'm now to be stand here to present this research paper titled I-Aware, Interaction-Aware Task Scheduling and for Reducing Resources Contention in Mobile System. Okay. In fact, with Moore's laws continue to work, the hardware performance of mobile system has been continually improved. Nevertheless, resource on mobile device remain limited. When mobile system needed to handle multiple tasks and application simultaneous time, these tasks are induced competition for different types of resource, resulting in phenomena such as slow system response and performance degradation. It ultimately leads to decreased user experience. The default task scheduling algorithm for Android is based on the CFS committed file scheduler. This in the Linux kernel, which determines the execution order of tasks based on their priority, CPU usage time, and real-time demand to allocate the CPU resources as far as possible, and ensure responsive tasks are processed in a timely manner. To ensure user experience of mobile system, the foreground application is different to minimize the impact of background applications. However, this paper observed the system service in the kernel and the framework layer instead of the background applications, which are major resource competitor. Next, we show our two key observations of this problem. The first is in mobile system, server tasks tend to have a higher possibility to be accurate when the user interact with the foreground application frequently, which induce serious resource competition. To demonstrate this, we performed our preliminary evaluation using two common settings: switch between short-form videos on TikTok and scrolling through the timeline on Facebook. Prior to run this application in the foreground, we cached 16 background applications to simulate typical mobile device usage. Then we keep the interaction in the foreground for 25 seconds to pause, followed by a frequent interaction in the subsequent 25 seconds. As shown in the figure A and B. From the solid orange line, we can find that the frame rendering demand for the foreground application increased when the interaction frequently was enhanced. At the same time, that is occupied by the increase in the CPU utilization for both front-end application and service tasks, as shown by the blue and yellow dotted line, which induced the serious resource contention. In fact, we can observe a similar phenomenon on different applications, and it can be noted that the service task occupied more than half of the CPU cycles. The observation too is, in fact, mobile devices often remain idle, resulting in underutilized resources as neither service tasks nor the foreground application frequently. To understand the resource characteristic in real usage settings, we investigated the usage characteristic of certain volunteers via mobile usage collector implemented on the Android platform for data collection as well as authorized. The survey of mobile volunteers showed that the device is idle most of the time. Resources are underutilized since neither survey task nor the foreground applications frequently run in this phase. Building on observation 1 and observation 2, we have formulated the key idea behind our approach. That is make use of the previously ignored idle period and schedule service task to run at that period. However, the design of this method will involve addressing three practical challenges. The first one is the minitableability and relativity of the user interaction state. For example, user may put their phone away or start browser short form videos right after scrolling through their Facebook timeline. Moreover, relativity implies that the distinction between idle and busy state is relative. With the same interaction frequency and workload, latency may occur on a low-end device due to insufficient hardware configuration, where it will not occur on high-end devices. There are two characteristics imply the capability to quickly and accurately identify and respond to changes in the state of user interaction is required in the approach. The second is the diversity of survey tasks in the system. The second challenge related to the diversity of survey tasks in the system. Even though a large number survey tasks may exist, not all of them can be executed in advance or delayed. Furthermore, different survey tasks may correspond to distinct schedule policy. The last one, the design should be lightweight and transparent. It's necessary to strike a balance between the performance of the method and its light and transparent design. Thus, we propose the aware interaction aware the task scheduling framework in a mobile system that aims to elevate resource contention by avoiding human-machine interaction rush hours. As shown in this figure, IVR consists of two components: the touch driver interaction identification model as TIM and the interaction aware the touch scheduling engine TSE, which address challenges 1 and 2 respectively. In fact, the TRM is tasked with timely and accurate identification of this current user interaction state, and the TSE schedules specific service tasks earlier or later based on the interaction state provided by TRM. The primary function of the TRM is to achieve a rapid mapping of measurable interaction feature to the abstract user interaction state. For example, normal, idle, or busy. In the idle state, it's typically for individuals to interact minimally with their device, particularly when the screen is turned off. In the normal state, users tend to interact with their devices more frequently, yet the user experience is not significantly impacted. In the busy state, the frequency of interaction can become high, that the system struggles to provide sufficient resource, ultimately resulting in a suboptimal experience. The figure visualizes the time map process. Yes, that's what the figure said. Specifically, TRM models user interaction representations so that measurable interaction features, including user interaction related information, like the user touch screen frequency and flag rate, and the system related information like user touch screen, CPU utilization, and available memory can be quickly mapped to the abstract user interaction state, which provides the decision basis for the targeted task scheduling of TSE components. To address the identification of targeted tasks required scheduling and their responding execution opportunity, I will introduce another critical component of TSE, this is interaction via the task scheduling engine. This engine modifies the occupability of tasks of target task in service task based on the TRM's identification results of user interaction state to achieve better scheduling. To implement its functionality, TSI incorporates two models, the system task and the server task sifter and the server task scheduler. First, the service task sifter need to identify whether the task has any dependency on the foreground application. If there is an inversion of communication relationship between the service task and the foreground application, the execution of the service task can be early or delayed for scheduling. We also identify all API that have three types of dependency: creation relationships, communication relationships, and shared relationships. Just like we then based on this, the service task finally output the result of dependency identification for all service tasks and stores them as, for example, service task name and the dependencies that pairs. After completing the sifting of the dependency, the next step is to optimize the scheduling of the non-dependent target task. Non-dependent target tasks in the service task schedule. This target task need to be further divided into two categories. One is prefixed target task and extensible target tasks. Prefixed target tasks encompass the most commonly used task widely executed on mobile system. Their scheduling optimization in the service task scheduler have already been predefined. Extensible target tasks supplement the limited set of prefixed target tasks as the time of non-dependent service task may increase. The optimization effect can be visualized in the figure, which elevates the resource competition by performing early scheduling and delay scheduling for service tasks in user interaction busy state. Moreover, I will have incorporated three strategies to ensure lightweight and transformed and transparent design. IVR is only triggered by the user touch event rather than run continuing in the background. This minimizes the interface overhead and conserves system resource when there is no user interaction for prolonged period. IVR also adapts a lightweight decision tree model for user interaction state identify and create model to accelerate interface. In the last, by developing a service task sifter, IVR can schedule only the necessary service tasks without having to consider too many service tasks. The experimental results of this paper are present next. The paper evaluates IVR on two Android smartphones, Oppo Find X3 and iQOO Neo 3. Mobile users often run more than 10 applications. So we pre-installed 16 popular applications on the devices to simulate daily usage. And the first game are evaluated for comparison. That is scheduling on Dual Smart Swap ZTT and IVR. That is the proposed framework. As shown in the figure, compare with two other policy, we can observed that IVR tries to meet the target frame rate as close as possible to minimize the frame rate degradation. With IVR, the application launch speed is improved by 28.21% and 27% on average, respectively. This paper shows the CPU usage of foreground applications and service task is measured for 70 seconds using different policy on different devices. The orange in the dotted line represents IVR. From this figure, it can be noted that when the IVR is used the CPU usage during the screen off period is higher than other policy. While the frequency of CPU usage exceeding 75% is significantly reduced during periods of frequent user interaction with the phone. Also, because I will reduce the frequency of CPU utilization be about 95% during frequent user interaction with the phone, it reduces the likelihood of resource contention. While we are provide better resource management, it comes with a set of trade-off. We also evaluate the runtime overhead introduced by Aware, including the memory consumption, CPU overhead, and energy consumption. The memory consumption and the CPU overhead of Aware at runtime are presented at this table. It can be observed for different foreground applications. Aware induced memory overhead of around 2.5 MB and additional CPU usage. Considering that energy consumption is a crucial factor in mobile system, we also conduct assessment of Aware of impact on battery life, since Aware is only triggered by user touch event. Rather than running continuing in the background, we evaluate its energy consumption during user device interaction. The evaluation results are displayed in the figure. Over the course of the 2 hours user device interaction, we observed nearly identical curves for the percentage decrease in the remaining battery with and without Aware. It suggests that additional energy consumption induced by Aware during user device interaction is minimal. We also use a statistical test to evaluate the impact of Aware on the device battery consumption during the period of no user experience. Specifically, we collected the standby power of device before and after interaction of Aware. The ball is our research work. At present, the mainstream work in this field is divided into 2 main directions. One direction is based on system resource scheduling, as much as possible to meet this need of CPU and memory resource for the foreground application. For example, the webs and PIFA. However, this work have some shortcoming. In contrast, Aware utilize the system-related and user interaction information to perform task scheduling and in advance during screen shutdown and usage. And the overhead is very low. And the other direction is from the perspective of task scheduling. Ensure task responsibility for the running of foreground application is prioritized. For example, Shut4Dog assigned a high priority to latency critical task. However, this work don't guarantee sufficient resource allocation for this time latency crucial task at the end of system resource. In summary, the form is the content of my presentation. I hope the research has sparked a new idea and the discussion. That's all. Thank you.
Thank you again for your presentation.
I think any question it's very welcome. But since I'm not the original paper, so I can't give a responsible answer.
Okay.
So
I think we should move on to the next speaker.
okay, thank you.
All right, I think our next talk will be on the paper, which is also the best paper candidate, one of the best paper candidates. Our next speaker is Li Ping Chang. And Dr. Chang is a professor at the Department of Computer Science at NYCU Taiwan. His research interest is on memory storage related issues for embedded systems, and he's going to present the paper titled Rectifying Skewed Kernel Page Reclamation in Mobile Devices for Improving User Perceivable Latency. Floor is yours.
Yeah, thanks for the introduction. Hello, I am Vipin. And this work is about how virtual memory management can affect user experience on mobile devices, especially on Android devices. So let's begin with virtual memory. Okay, so virtual memory has been a standard technique for modern operating system to improve the degree of multi-programming. So with virtual memory, we can run a lot of apps at the same time. And here shows we have two types of virtual memory pages in the physical memory. The first type is anonymous pages. They belong to process heap, process stack, and some belong to shared memory. Okay, that is anonymous pages. And we also have file pages. They are from regular files in file system, and they are created by read-write and the memory map system calls. So with virtual memory, when the memory pressure becomes high, the kernel must selectively replace virtual memory pages from the physical memory so that the kernel can reclaim free space for new applications. But here, as we can see, the two different types of pages, they are backed up by different devices. Anonymous pages, they are backed up by the swap device, and the file pages are backed up by the file system. So here, when the reclaiming of free memory space, the kernel must decide how much free space is reclaimed from anonymous pages and how much from file pages. This question is challenging because the cost of page faults on these two types of pages are different. For example, for page fault on anonymous pages, these page faults are slow because page faults on the swap device, their IO pattern are highly random, and swap activity usually involves small and random IO operations. So that is why page faults on anonymous pages are slow. But on the other hand, file system can use many useful techniques such as file defragmentation, file space pre-allocation. So file pages in file system, actually, they are highly sequential. And page fault handling on file system is very efficient, provided that you have appropriate pre-paging techniques here. Okay. So to deal with the different page fault cost, the kernel provides a parameter called swapness. If swapness is set to 100, it is a value between 0 and 200. If we set swapness to 100, then the kernel is expected to reclaim from the two types of pages equally. Okay. But in many real systems, as we can see, actually the swapness is set to 60. Why is that? Because the kernel think file pages, they are page fault here are much efficient. So the kernel become more aggressive on reclaiming free space here. And the kernel thinks, oh, anonymous pages are expensive, so it would like to catch more anonymous pages in memory. So we are curious about whether the setting of swapness to 60 is that appropriate for mobile devices. So here we are focused on a very common user operation, that is app switching. App switching here. So for example, we can watch YouTube video and then switch to Facebook and then switch to the Chrome browser as the foreground app. Okay, so here we have app switching, and the latency between the apps is the app switching latency. And this latency is highly perceivable by the user. Okay, and here we observe the total number of page faults during app switch. And here we can see there are a lot of page faults during app switch. And the switcher latency is high when the page fault number is large. Okay, so that means there is a strong correlation between app switching latency and the handling of page faults. Okay. And now here, so we measure the page fault latency on swap and on file system. And first, we put both the swap and the file system on flash storage. Okay, because Android is based on flash storage. So indeed, we find that page fault on swap is it takes longer time to handle page fault. It is about 5 times lower on swap than on file system. Okay, but let me emphasize, Android is swap on ZRAM. Okay, not on flash. So ZRAM is a compressed RAM disk. So swapping on ZRAM, actually, it does not involve I/O at all. Okay, so here we measure the page fault cost again, and we found that, well, now page fault on ZRAM swap becomes about 30 times faster than page fault on file system. So this figure changed a lot, right? So we further measure the total number of page faults and how much data we read from anonymous pages and the file pages, and we can see that the total number of page faults on anonymous pages are much lower than that on file pages. That means the kernel really doesn't want to swap out and swap in anonymous pages because it believes anonymous pages are expensive, but actually that is not the case in Android systems. Okay, so that means ZRAM swapping actually it is underutilized. So how can we swap more on ZRAM to improve the app switching latency? So our design consisted of 2 parts. The first part is it is a new kernel thread called Sweeper. Sweeper will monitor the app switching event. So when app switching has been detected, it will scan new anonymous pages and then decide whether their reclamations, should they be prioritized or should they be delayed. Okay. So this part is to identify reclaimable anonymous pages and reclaim these pages as soon as possible. And the second part of our design is adaptive swapness. So the objective here is to increase or to decrease the swapness according to the workload needs. So it is an enhancement to the existing K-swap-D kernel daemon. So with it, K-swap-D will monitor page 4 on ZRAM and on file system so it can adjust the swapness level accordingly. Now, this is our first strategy. It is called proactive anonymous page recamming. So here is a very interesting observation that we measure the anonymous memory size, that is the total size of anonymous pages of Android apps over time. And as you can see, the anonymous memory size increases over time. It is very interesting because, for example, here, this is Facebook app. And every time when you bring the Facebook app to foreground and use it, every time you do this, its anonymous memory size grows a little bit. So the anonymous memory, total anonymous memory size in the system grows bigger and bigger and bigger. Okay, we call this phenomenon as anonymous memory inflation. We call this inflation because we further identify that about 20% to 40% in the anonymous memory, they are used in the current app cycle, but they are no longer used in all the subsequent cycles. That means this memory are one shot, reference once, and they are abandoned. Okay, so our strategy is to identify these pages and reclaim these pages as soon as possible. So here is an example. We have a 3 app use cycle. The first cycle is involves the YouTube app as a foreground app, and the second cycle has Chrome as a foreground app, and the third with Facebook. So here we have 2 pages. The first is page A. Page A has been created in the first cycle by the YouTube app, but it has not been referenced in the second cycle. Okay, so here our sweeper thread. Here, this one. Our sweeper thread will classify this page as dormant because it has not been used in the full cycle. Okay, and the sweeper believes that it is an abandoned anonymous page. So what it does is to forward this dormant page to the inactive list to prioritize its reclamation. Okay, so it can be reclaimed as soon as possible. So here is page B. Page B is referenced in the first cycle and also the second cycle. So our sweeper will forward this page to the active list. That is to delay its reclamation because it has been used in multiple cycles. Okay, so it should not be a dormant page. Okay, so our strategy is to identify dormant pages and prioritize their reclaiming. And here, this mechanism looks like a page level design, right? But this mechanism is based on existing debugging bits on pages. So basically, there is no extra overhead for this mechanism. This is the second strategy of our proposal. It is adaptive swapness. So swapness is between 0 and 200, and the neutral level is 100 in the middle. Okay, so the kernel thread K-swap-D begins with the neutral setting, that is 100. And then every time when K-swap-D is invoked to reclaim free memory, we run a few checks. The first one is if ZRAM is heavily utilized in terms of space. Okay, so if zero is nearly full, that means we have swapped too many anonymous pages to zero. Okay, so in this case, we will reset swappness level to 100 so that the swapping activity can be slowed down. Okay, and the second test is if there are too many page faults on valuable file pages, that means we have been too aggressive on file pages. Okay, so we will increase the sharpness level to reclaim more anonymous pages and to catch more file pages. Yeah, right. So here we will increase sharpness. But here also has a question here. How do we know that this file page is valuable? It is determined by the refaulting event. Refaulting means that here, for example, a new file page has been created and the reference and promoted to the active list, but somehow this page get replaced. And later, soon later, it is refaulted and go back to the main memory. So this is a refaulting event. If there are too many such events, that means we have been too aggressive on file pages. Okay, so this is a second test. Now here means that everything goes well. So we will restore the sharpness level toward the neutral setting of 100. Okay. So now is our experimental result. Our experiments are based on Pixel 4, and we have a remote PC as a debugging console. And in the middle, there is a USB power meter that is to collect the power consumption of the Pixel 4 phone. Okay, so here Pixel 4 has 6 GB of RAM, and the default setting of the DRAM size is 3 GB. But notice that this is a uncompressed size. Okay, so the actual memory requirement is much smaller than this. And the DRAM space is part of the 6 GB of RAM. Now, here we have a few different workloads. The first one is a light one, and the second one is a heavy one. This one has a big demand for file pages and also on anonymous pages. Right. This one is the most important workload in this study because it imposes the heaviest memory pressure on the virtual memory system. Right. Here shows the app switching latency. AS here stands for our adaptive sweeper design, and KS stands for the original kernel with a static sharpness level of X. Okay. Now here in this figure shows the app switching latency. So the smaller the better. As you can see, our AS is the white bar. Our AS performs the best under all the cases, and under the most heavy workload W2, the reduction on the app switching latency is about 40%. Okay, that is a big improvement. If we analyze the page faults on different types of pages, we can see that the original kernel has a lot of page faults on file pages. But with our adaptive sweeper, we traded a lot of page faults on file pages for anonymous page faults because swapping on DRAM is fast. Okay, that is why we can improve the latency. Here the original kernel is highly sensitive to the sharpness level setting, as we can see here. The left 3 bars are with the original kernel. So under workload 2, the sharpness level of 199 is the best, but under workload 3, the setting of 180 is the best. So that means the original kernel is highly sensitive to the workload, but anyway, our method is adaptive to these workloads. Yeah, right. So this is analysis of runtime overhead. We are curious about whether our method has impact on runtime performance. So we use 2 metrics. The first one is janky frame ratio. A frame is janky if it misses the next vsync event. That means its rendering has been delayed. Okay. So here we can see that the janky frame ratio remains the same with or without our approach. And here is the power consumption normalized to the original kernel. So we can see that the energy consumption is not affected. That means our runtime overhead is very small. So here, finally, it's my conclusion. So this work is motivated by the availability of fast swapping device. For example, in Android, we have a ZRAM for swapping. And in the future, we may have a persistent memory as the external swapping device. So how does it affect the handling of page fault? And how does it affect the user experience? Okay, so we have 2 important findings. The first one is Android apps produce a lot of reference ones, anonymous pages, and they accumulate in the main memory and eventually fill up the physical memory. Okay. The second is the existing kernel really does not want to reclaim anonymous memory because it thinks page fault on anonymous pages are so expensive, but that is not the case in Android. Okay. So our approach is to identify and to reclaim dormant anonymous pages and then adjust sharpness level adaptively. Okay, that is all my talk. Thanks.
Thank you very much for this nice presentation. I think we have a lot of time for questions. So would like to ask, please.
Thank you very much, Liping. So I have a question, very naive as usual. So the Android apps suffer from anonymous memory inflation. So if we don't switch from one application to another, if we stay on just one and stay, do they suffer also from this page that they create and they don't use anymore? Or is the fact that we switch that makes them lost somewhere?
You mean if we do not switch between apps?
I am Facebook and I'm staying on Facebook. I don't.
Okay.
What is the memory behavior?
Yeah, there is still negative effect here because as the longer you use an app, the more serious the memory inflation is. So next time you eventually switch to the second app, the delay will be very high.
Okay.
Because you accumulate a lot of, I call dormant pages in the main memory.
So there is a problem per app, and after, if I want to switch, this problem accumulate and gets worse and worse.
Yes, exactly.
That's my question. So one first step wouldn't be to say write apps that are better coded, because it means that the code is bad. In fact, the Facebook app code is bad.
Right.
You try to correct a bad code, in fact. So
yeah, blame it on them. Right. Exactly, because I think they don't handle this. I mean, Facebook engineers, they don't face this.
Yeah,
this problem because let me explain. There is a final result in Android, that is to kill the process. So sometimes you use an app and switch between them. Sometimes you feel, oh, this has restart. How come it restart? Just like you first launched the app. That is because the app has been killed, because it produced so many domain pages and it becomes so huge in the main memory. So it got killed. Okay, so I would say that that is not a serious problem that they want to handle at this time, but eventually they have to improve their code, right?
Yeah, that's the feeling I have. So maybe it would be important to feedback to them some good practice of coding.
As you can see, every app has this phenomenon. So
Yeah, thanks for your talk. I think you made your point, right? It's very clear that the impact of swappiness, then it's very relevant on the performance of the application. Then my question is, do you think there's space to have some compiled based assistance to pre-identify the pages that are more likely to be dormant, since some information can be extracted from the application rather than pushing for certain programming models that could, be difficult to accept in this domain?
yeah, right. You mean, is there any room for compiler to deal with this problem?
Identify what are gonna be the dormant pages and then explicitly inform Android on the fly that you look, I need this page, but more likely it's gonna be dormant in a few milliseconds, right? Rather than pre-identifying pages, creating the application as a black box components.
Right, you are right. In this work, it is like we are fixing some problem created by them. But actually, yes, we can. I will not use. I mean, there are many techniques can do this. For example, we can use M-advice, this system call, to tell the kernel, well, this memory region, I may not use it anymore, and the kernel can actively reclaim this memory. There is this operation available. I mean, but they this app developer, they don't handle this problem.
Okay, thanks.
Okay.
Do we have any other? Yes.
Great talk. So I was wondering that is there any downside to your approach? Because it seems like, quite intuitive that we should recycle these anonymous memory pages, and Android is not doing that. Why is that? I mean, is there anything that we are losing by doing what you are doing?
Yeah, you mean, is there any negative effect on recycling these pages? Yeah, there should be, but compared to the compared to the cost of paging in a lot of file pages, because the original kernel, they are too aggressive on reclaiming file pages, so the proportion of file pages in the main memory is so small. I mean, here, as you can see, about 25% of the main memory is for file pages. Why so small proportion? So, I mean, if you reclaim these anonymous pages, is there any negative effect? Yes, if we, if the pages are again used by the apps, there could be more page faults on anonymous pages. Let me think. I should have some numbers here. Oops. By the way, according to our statistics, the probability of another page has been identified dormant, but later used again, the probability is so small. Okay, so there's no significant impact here.
Yes, please.
I have a related question. So it seems that in your approach, if the page is not referenced in the cycle, then you put it into inactive list. So have you considered the case where we keep switching application back and forth all the time? So in that case, so maybe I'm in YouTube, I switch to Facebook and back to YouTube. And the cycle is the time that you use one application, right? So in that case, if you just don't put it into inactive list, then next time you have page false again, right? So
Right.
how would the algorithm work in that case?
Right. Actually, there are some the details are in the paper. There are some threshold. The app cycle should not be too short. Or if the cycle is too short, then we may produce some incorrect prediction or classification on domain pages. Okay. And if a cycle is too long, on the other hand, we may break the cycle into a few intervals and to do domain page classification and reclamation. Okay, so the cycle should not be too short or too long. Okay.
I see. Quick follow-up. So do you think your technique will be able to be translated to other kind of devices beyond the Android?
Excuse me?
We work in similar strategy works in other kind of devices, not just Android, like maybe iPhones, something else.
You mean, what do you mean by copyright?
Other types of embedded device, not Android.
Okay. I cannot answer that question for now, but I mean, we can have some discussion after this.
Okay. I think it's time to move on to the next talk. Thank you very much. So our next speaker is Yusuf Kwon. He received a bachelor's degree from School of Electronics Engineering, Kwang National University, South Korea in 2019. And he is also pursuing PhD at the same department with a degree with the AI embedded system software on chip laboratory, School of Electronic and Electrical Engineering. His research interests include both software for MCUs and hardware processor design for edge AI. So he's going to present a paper titled Efficient Partial Weight Update, the techniques for lightweight on-device learning on tiny flash embedded microcontrollers. Hello, is yours.
Thank you for introducing. Hello, my name is Yusuf Kwon from Kyung National University, South Korea. It is an honor to be able to present at the Emsoft conference. This paper is about implement on-device learning using microcontroller, which has a tiny memory constraint and low performance processor. So, starting to motivations. As the demands for edge AI continues rise, research focused on enabling machine learning applications to run on resource-frugal microcontrollers device is increasing. So machine learning applications can be categorized into three components. First one is model architecture, and second one is backbones for machine learning computation, and third one is weight parameters. So these components are loaded into the on-chip memory of the microcontrollers in binary format. So in this paper, we focused on the weight parameters among the three components, how they are stored in microcontrollers on-chip memory. Microcontrollers offer two types of on-chip memories. The first one is flash memory for non-volatile memory, and second one is SRAM for volatile memory. We need to consider the different characteristics existing in flash memory and SRAM. So to make a binary fit within a memory constraint or the mitigate performance decrement. So most of the microcontroller SRAM size difficult to fit machine learning applications. So we need to partition model parameters between two memory types. This figure shows fundamental neural network architecture, which is composed with fully connected layers, while SRAM offers more flexible read and write access compared to flash memory, but it has SRAM has a higher cost compared than flash memory, so resulting in smaller storage capacities than flash memory. Consequently, it is inevitable to store a part of the weight parameters in flash memory, which exceeding the SRAM's capacity. However, flash memory has a critical limitation. To write data on flash memory, page-wise erase must be preceded. But we want to implement on-device learning on microcontrollers, so we also need to access our flash memory, right? Because we update the weight parameters which is stored in flash memory. So if it can minimize update of weight stored in flash memory, we can also decrease the high cost flash memory access. We propose a technique which updates part of the weight selectively. The figure first plots input layers gradient delta between each sample data, which is input to neural networks, on using a multi-layer perceptron, which is using an MNIST dataset and fully connected layers. So we assume that pixel which has a higher gradient delta makes more contribute to accuracy. So we defined a threshold value for a gradient delta as written in TH capital. Then update weight only when the gradient delta exceeds a certain threshold value. This is an overview of the weight update process. We have modified the linker script to make that the rows of the weight matrix fit in within the flash memory page size of the target device. Gradient computation can be calculated through the in-place vector multiplication of the activation and the error from the next layer. We compare the average gradient delta for each weight row, whether it exceeds a predefined threshold, and we only perform updates to the weight stored in the certain flash memory page when this condition is met. So this is an experimental result. When compared with the state-of-the-art papers that implement on-device learning on a tiny microcontroller, our approach achieved the same level of accuracy on target on a larger dimension MNIST dataset by significantly reducing the memory requirement. And the amount of the entire weight is about 92 kilobytes. Without our scheme, when we update the whole weight with iterative flash memory access, we've got 77.4% of accuracy. But using our scheme, the accuracy is reduced by only 1.3% when only 18% of the weight is updated. We have defined an evaluation metric, which is the area power delay product, which is written as APTP. To evaluate the proposed technique, lower value is better. So we measured application execution performance while taking account of microcontroller's logic area. So when our approach technique was deployed on our target device, the Cortex M0 Plus, we achieved a lower area power delay product and higher accuracy compared to the high performance Cortex M4 processor. So I wrap the presentation. We propose a technique to select the weight partial updated region based on the delta of gradient average at runtime. Also, we demonstrate the feasibility of the proposed scheme deployed on a Cortex M0 Plus microcontroller with only 20 kilobyte SRAM and 192 kilobyte of flash memory. Thank you for listening to the presentation.
Thank you. I think we have room for just one question, very fast question. Do we have any? Maybe I can ask, did you try any other data sets? I mean, you presented that like avoiding update of some weights will be still beneficial. Do you have any justification by using other data sets and other?
Thank you for question. Currently, I only evaluate my proposed technique only with Emsoft, but because our target device is only has a 20 kilobyte SRAM, so this memory constraint is quite so tiny to apply other image data sets such as LiPAR or ImageNet. So that is our future plan to apply other data set to in this scheme. So,
thank you very much. Thank you again. Yes, our next speaker will be joining online. So, Xiong Huang, who is a graduate student at Xiamen University in China, and the research direction is about the performance of energy saving optimization of Android operating system.
Hello, ladies and gentlemen. My name is Shixiong Huang.
I think we can start. Yes.
Hello, ladies and gentlemen. My name is Shixiong Huang, and I will introduce my work. Rendering redundancy consumes a lot of computing resources in mobile devices. Eliminating redundancy can effectively improve system energy efficiency. However, as the promise of redundancy elimination, the existing redundancy identification methods affect the final performance because of the exclusive cost. In this article, we propose the CLEAR, a high-performance cross-layer method for eliminating redundancy. The Android rendering process is the entire process from the accuracy of user events to the rendering of frames. The CLEAR is located in the draw frame part of the rendering process. Draw frame is preceded by the user events that triggers the new chip update, followed by the conversions of intermediate commands into specific OpenGL draw instruction to the GPU. CLEAR breaks down the rendering redundancy detection process into two collaborative levels, namely the first rough detection of the Java layer and the process and the detailed detection of the native layer, which reduced the computation amount by about 2/3 compared to the precise detection alone. Why is that? Because the preceding Java layer coarse grain detection screens out 78.7% of the random nodes. This data is an experimental data related to the specific application scenario and the user operations. We designed a detection algorithm based on XOR operation at the Java layer, which performs XOR operations on the types and the parameters of JOP called in one frame, recorded it as current result, and compare it with the results of past results in the previous frames. This method can quickly screen on less redundant nodes, and the XOR operation is relatively simple and fast. Its memory overhead, time overhead will be very low. In this way, the subsequent native layer only need to accurately detect the remaining random nodes rather than detecting all of them. We tested on a Pixel 4 font with a version of the most popular Android 12. Test the typical top scenarios, including desktop, TikTok, WeChat, and the results show that CLEAR can reduce frame drop rate by 14.5% and save SoC energy by 5.1%. In addition, the CLEAR time overhead is less than 3,000 of the rendering time, and the memory overhead is only an additional 9 bytes. This is an work in process paper, and there is a lot of work to optimize in the future. In the future, we will look into more fine-grained detection and then consider adding sophisticated detection methods. Thank you for listening.
I think we have again room for one question. Do we have any? Speaker is not here. Okay. Okay, then it's time to conclude the session. Thank you for joining, and I enjoy everyone. I wish everyone enjoyed the rest of the conference. Thank you very, very much again.